Color blending. So when we're talking about color blending, there is this general blending formula. It's an equation to blend together overlapping pixels. And this is an extremely important equation in blending, so let's look what it does. First of all, we have two parameters, source and destination. So source is the pixel that is put on top of the destination pixel. And we can think about it this way, that the fragment shader is kind of like a source, like a water tap that spits out pixels. And these are source pixels. And then we have this color buffer that is the destination. These source pixels, they go to the color buffer to the destination. So when we're blending together these pixels, we need to be very certain on what is the source pixel and what is the destination pixel. The source pixel that comes from the fragment shader and the destination pixel that is already in the color buffer. To combine those two color values, there is this function. And this function can be addition, subtraction, reverse subtraction, min or max. So you can configure what kind of a function is being used to combine those pixels. But note that not any function can be put there, only those 5. Then we have these factors. So both the source and the destination are multiplied with some configured factors. And these are again something that you configure. So it could be like the source factor might be 0, might be 1. It could be also the alpha value of the source color, or maybe the destination color itself. And the same for the destination factor. Different combinations of these factors and these functions give us different blending modes. The first blending mode that you probably know is conventional alpha blending. So this is your regular traditional transparency blending. You have an alpha value that specifies transparency and you put two images or two pixels together by accounting for that alpha value. And the blend equation is configured this way. The function is plus, the source factor is source alpha. So the source color gets multiplied by its alpha value. And then it's added to the destination pixel that is multiplied with 1 minus source alpha. So both the source and destination pixels are blended together linearly by using the source's alpha value. For example, down here, we can see that we have some opaque pixels, so this one has alpha 1. We have some fully transparent pixels, so this one has alpha 0. And then we have some semi-transparent pixels, like this one with alpha 0.5. Our destination, our color buffer, always has this alpha 1. Those are already blended pixels, they're all opaque. When we combine these source pixels with the destination pixels, we just use the source alpha to combine them. For example here, well, source alpha is 1, we take the red color, the destination gets multiplied by 1 minus 1, so this becomes 0, and we end up with this red color. A very similar thing happens with this green color, where we had a fully transparent pixel, so its alpha was 0, so we have 0 times whatever was in the source, currently it was 0, 0, 0, and then we add 1 minus 0, the destination pixel. But a more interesting case is down here. So when we have alpha 0.5, we take 0.5 times the source, 1 minus 0.5 times the destination, and we add them together. So we end up with 0.5 in red, 0.5 in green, 0 in blue, and alpha 1. Alpha always becomes 1 after this blending. Now there's an issue with this conventional alpha blending. When we upscale, downscale, or move the source image, we use bilinear interpolation. And with bilinear interpolation, some things go a bit wrong. For example, here we have taken a 3x3 area and enlarged it to a 4x4 area. And all these values are bilinearly interpolated from the previous values. The issue that happens here is that some of these values get a wrong color. At the moment, they're all becoming a bit darker than they should be. This is because we had this 0, 0, 0, so the black color in the fully transparent pixels. We are interpolating both the color and the alpha value. So both the color gets darker, gets mixed towards black, plus alpha gets lower, gets mixed towards 0. So while the pixels are getting more transparent, as you would expect, they're also getting more darker. And this is called alpha bleeding. Now if you would have different colors in the transparent pixels, for example white, then they would get brighter, they would get more towards white. So they would always move away from the color red, well, unless your fully transparent pixels are all of the same color red as well, but this is usually not the case. And there is this example in CGLearn where we have this red donut shape that is a transparent image, so some of the pixels are transparent and well the red is not. And if we zoom in, we can see that there is this white alpha bleeding happening where the transparent pixels are being interpolated. Same thing happens if we zoom out. And there is this other blending mode, pre-multiplied alpha blending, that fixes this issue. So if we zoom out or zoom in, these are smooth red circles without this alpha blending alias. So pre-multiplied alpha blending. So what this does is it first pre-multiplies the RGB part with the alpha value. So there are these constraints on the color values. For example, here we have this red 1, green 0, blue 0, and alpha is 0.5. With pre-multiplied alpha blending, this would be an invalid value. Instead, we want to multiply this 0.5, this alpha, already into the color. So this becomes 0.5, 0, 0, and 0.5. We still, of course, keep the alpha value here, but the color, the regular color that you would have with conventional alpha blending, that would be multiplied with the alpha value. This also means that if you were to now render these images that have the pre-multiplied alpha in them with conventional alpha blending, then that would give you a wrong result. But now with pre-multiplied alpha blending, the interpolation no longer causes this alpha bleeding issue. We can see here that while the colors and alphas are both interpolated, the colors are what they should be. And with pre-multiplied alpha blending, it also means that we cannot have anything else than black as fully transparent pixels. You cannot have 1, 1, 1, 0, because that would have to be multiplied by alpha, and when alpha is 0, then 0 is the largest value you can have here. Similarly, when alpha is 0.5, then 0.5 is the largest color channel value you can have for those pixels. When we have a picture that has the pre-multiplied alpha blending encoded into it, so every color has been multiplied with alpha, we have to use a different blending equation to blend it with the destination. And this different blending equation sets the source factor as 1. The destination factor still stays as 1 minus source alpha, but because the alpha is already multiplied into the source, then the factor here will just be 1. And to combine this source with the destination, well, we just apply this formula now. So the source, which was 0.32 in red and zeros in green and blue, well, this just gets multiplied by 1 and then added to 1 minus 0.32, the alpha of the source, times the destination, thus resulting in the blended value that we would expect. Now to explain this alpha blending a bit more, we can look at the blending formula for conventional alpha blending. There we had source times source alpha. So we have colored multiplied with its alpha. But now let's say we interpolate that value before we blend it. So we do bilinear interpolation, we move it or we upscale it or we downscale it. What matters is that we're multiplying both the color and the alpha with some interpolation factor, and let's call it gamma. So we're changing both the color and alpha together during this interpolation. And there you can see the problem. Because we multiplied both the color and alpha with this interpolation factor, then it gets kind of multiplied twice. Because we multiplied alpha with it, but we use this new alpha, this interpolated alpha, in the blending equation later on. So we're multiplying this gamma into the source through source alpha during blending, and we have also used this gamma during the interpolation already and changed the color by using the gamma on that as well. So we kind of use this gamma twice, and because it's a number 1 or lower than 1, then using it twice will kind of diminish the color of the source pixel. That is why when pixels are alpha bleeding, then the color is kind of diminished and you get some kind of other aliased color there. Now with pre-multiplied alpha blending, the alpha is already multiplied into the color and we don't multiply it in the blending equation. So there we just have 1, and although we transform the alpha while interpolating, we're not using the transformed alpha in this particular multiplication, thus avoiding gamma getting applied twice. There are two other useful blending modes. One is this additive blending. So if we want to add different colors together, we can set the blend function to have the source factor as 1, the operation as plus, and the destination factor as 1 as well. So this just results in two colors being added together. This is how light works. So if you want to have some sort of a beam of light or some visual effect that would look like light, or maybe you have a sprite of some fire, or you are procedurally generating some pixels that should represent fire and light that comes from fire, then you can use additive blending to create this interesting effect that kind of looks like light. The second one is multiplicative blending. So there we set the source factor to 0 and we set the destination factor to source. So that's the color. so we're multiplying both of those two colors together. This is how, well, pigments work, but you can do all sorts of interesting effects with it. So if you want to have like an overlay for shadows, for example. Here's a picture of World Remade by Janus. So what he did there was he created this overlay that was mostly dark, but the locations where he had light sources would contain more white areas in that overlay. And when you multiplicatively then blend this with whatever you already have drawn in your game world, then some areas will get darker because they're multiplied with lower values, and some might stay the same because they're multiplied with 1 or values very near 1. So from this video you should understand the general blending formula, the source and destination colors, the configurable factors, and the equation. So you can configure the equation, how should you combine the source and destination, and then factors for both the source and destination. You should now also understand alpha blending, the conventional alpha blending and what issue it might have, and the pre-multiplied alpha blending and how that avoids this issue of alpha bleeding. You also saw two other useful blending modes, additive and multiplicative.